You know, I record my morning class and I record my afternoon class, so it'd be interesting to just watch the videos and see which one I'm actually better at. You know, if my early morning self is more on the ball, or if my afternoon post-lunch self is better off. Mm-hmm.
You're seeing yourself like auditioning.
Exactly. Hey, can I ask you a favor?
Yes, sir.
I have one eraser in here, and it's terrible. The one in the back is broken. This one is now broken. Could you go to another classroom and just blatantly walk in and steal their eraser?
You mind if I just get a rack?
Oh, sure, yeah, if you want to use a rack. We'll try it out.
If it doesn't work, let me know.
Sure.
Sorting. That's the first time.
Yeah, here's good. Ooh, you can come up with very nice. Back to Arabs, that's really good. And you know it'd be a fun prank because if by the time we got back, we were all hiding. We all just left. Shut the lights off. We could pull it off.
It's all like you standing right there just doing what the heck happened.
Okay, take one more minute, wrap up here. I'm going to keep that up there, so if you need more time to write it down, you can always write it down. Let me go ahead and quiz you all then. There's 6 of you, there's 6 questions. So what happens in this transformation, Valeria? It's inside, so it goes
to the left.
Left 3, exactly right. Emily, what happens in this one? It's outside, so it's
It goes up.
how much? Up 5, very good. Maybe it's outside, so it's
Down to.
down 2, perfect. Omar, it's inside and outside. Omar, what's the outside number mean?
Goes right to.
Yeah, that goes right 2 and then up 3, very good. And then Hector, this is out in front.
I'm in front.
Oh, what?
On the x-axis.
Yes, no, that's true. Now, in your notes, you'll notice that it says reflect across the x-axis. Let's just clarify that real quick. If I take a smiley face and I reflect it over the x-axis, then this is my mirror line. And if I reflect my smiley face, then that smiley face gets flipped down here, which is the same thing as flipping it upside down. So your notes on the packet, it says reflect across the x-axis, which means flip it upside down. Whereas if you look at there's another line on there when you put the negative on the inside, and that's reflecting across the y-axis, which if the smiley face was here, it would reflect across this line and go over here. So in any case, we've got flipping upside down, and then we could call this flipping right side left, or just flipping across the y-axis. Okay, and then the last one, Gabe, what's number 6? What's happening there?
Would it be stretching vertically by 3? How do you?
You can say 3 times as tall. You can say stretching vertically by 3. Absolutely. So on the next, on the next page, these we now want to write down the formula. So let's try this out. At number 9, all of these we're talking about the square root function. So my parent function is the f of x equals the square root of x. That's my parent function. And now I'd like to do all these transformations. So in number 9, we want to, you can start out by writing f of x equals a big square root. We know that that's the basic idea. So we need to shift it right 2 and then down 3. So if I want to shift right 2, what am I going to, I'm going to do x minus 2 inside the square root. It has to fall completely under the square root. If you wanted to be really cautious, you could put that in parentheses. To say, hey, that's what's under my square root. And then we want to shift it down 3. So if I want to go down 3, I'll subtract 3. And that's what our function looks like. Now, of course, that's just a function. It's very important to always, any function you ever look at, might as well graph it. Here's my parent function, SQRT, by the way. SQRT is how you do a square root, SQRT. So that's my parent function. And notice this little point right here at the origin, I'm going to call that my pin the tail on the donkey point. That's the point that I'm picking up and moving around. So now if I really did want to shift this graph right 2, down 3, I would do SQRT of x minus 2, and then outside the square root, minus 3. And sure enough, I went right 2, down 3. What moved right 2, down 3? This point right here. Because once you move that point, then you just draw the graph. Okay, next one. Reflect across the x-axis and then shift up 1. So we want to reflect across the x-axis. That means you might want to draw something to visualize that. If you draw a smiley face and flip across the x-axis, that means it'll flip upside down. And if it flips upside down, that means we're going to put a negative in front. So now, number 10, we have f of x equals a square root, and we have a negative in front because it flips upside down. And then we also want to shift the whole thing up 1. So if I want to go up 1, what would I do? I'm just going to write plus 1 outside of the function, right? Outside of the function. So let's check to see if we did it. I want to flip it upside down and shift right 1. So I'm going to flip it upside down, SQRT, and shift it up 1. And there we have it. Now notice, what shifted up 1? The origin point, the vertex point, the pin the tail on the donkey point. That's what shifted up 1. And then the thing got flipped upside down. Okay, how about number 11? Yeah.
Did we do number 6?
We did do number 6. In fact, I thought
What was it?
number 6 was just, what was number 6, folks?
3 times as tall or stretch rate.
Yeah, 3 times as tall. That's right, Gabe said it.
Or stretch rate.
Yeah, it's a vertical stretch. Okay, so number 11, a lot is happening here. So we start by writing down f of x equals square root. So shift left 1. Oh, go ahead.
Oh, no, I was.
You want to? No.
So
Just go one step at a time. How do you say shift left 1?
So you put, I put parentheses,
Yeah.
but it'd be x plus 1.
Okay, very good. So far, that's for sure what we have in there.
Reflecting across the y-axis. So this is, so it'd be a negative x.
There would be, and the big question here is, would we put the negative there or next to the x? And we'll clarify that in a second by actually graphing it. Okay, and then last?
Plus 2 outside,
Yeah, plus 2.
outside of the square.
Now, folks, this is a tricky one because I did not put this in my formula. We don't often flip something, right and left by putting a negative sign in there with the x. But that's what the answer to this one technically would be. If the negative sign is outside, it's a vertical flip. Whereas if the negative sign is inside, it's a horizontal flip. Well, so let's check. Let's do this as an experiment. This is what makes graphing calculators so cool, is that you can do experiments, real-time experiments, and just try things out. So what we have here is the square root, and then it's x plus 1, and then we also have plus 2. And now the question is, should we put the minus sign in front of the parentheses, or should we put the minus sign on the x? Now, first of all, notice, folks, can you see that there's a difference? That's the minus sign in front of the parentheses, and that's the minus sign in front of the x. That's a very subtle difference. Let me just show them both to you simultaneously. Here's the negative sign in front of the parentheses, and there's the negative sign in front of the x. So now which one answers the question? I want to shift the whole graph left 1. So which one of these starts at left 1? The blue one. So already it's got to be the blue one, which is the negative sign in front of the x.
Okay.
Yeah, in front of the parentheses. Yeah. Okay, so there we have it. Now again.
So the only way to find it, to find the right answer is graphing it?
No, not graphing it. My formula here could be a little more specific by simply putting a parenthesis there and then putting a plus or minus there. And then saying that is the flip right left instead of flipping upside down.
stops there.
Yeah, well, bottom side up, that would still be up and down, right? So left, right, yeah. Yeah, this doesn't happen very, very often. I find almost every problem in the world, you're putting plus and minuses here, but not so often in here. So I was going to try to get away from not talking about it. But yeah, it would go in there, but outside the parentheses surrounding the X shift. Yeah. Okay, well, very nice, very nice. Let's try the last one, or everybody, better yet, try the last one on your own. Write down what you think it would be. Start by, always begin by just writing down something. Start somewhere. Write down f of x equals square root symbol and put in what you do know. That's always a great way to start, is start with what you do know. There's going to be an x in there. And then you want to shift left 3, a vertical stretch by 2, and shift down 4. So start with what you know. Yeah, that's right.
I'll make sure to write the 2.
In front of the square root. The f of x is just going to stay f of x. We're creating a new function. Yeah, exactly.
So,
Yeah, let's do it.
Yes?
Okay. Yeah, I think you got it there.
So negative.
So as you're all writing down these numbers, you might be thinking to yourself, oh geez, is that right? Oh geez, did I do it? So how would you test your own hypothesis if you're right? You just graph it. You just graph it. But it looks like a lot of you had the answer shifting left 3 means x plus 3 inside the square root. And shifting down 4 means you wrote minus 4. And then a vertical stretch by 2 means you put a 2 up front. That's it. By the way, folks, this little notation I did right there, I forgot to mention this in my other class because I never do it myself, but some people put a little down tick right there to denote the end of their square root. Because people can sometimes be so sloppy that they write things like this. And you're like, that kind of fades away. What's going on? So if you want to be very conscientious, you would put a down tick and say, that's x plus 3. That's the end.
Is that in a lecture hall?
What?
Is that in a lecture hall?
Do I say that in a lecture hall? I don't know. What do you mean? Have I? I've actually never seen anyone do this.
I do.
Oh, do you?
Yes.
Great practice.
Well, I meant the other one where they just fade.
Oh, yeah. Lecture hall, exactly. You're like, what? What did I just write? Okay, well, very nice, folks. So you've just did, what did you do again? Oh, did it work?
Yeah.
Good. Okay, last then is we're going to graph a couple of these. So when you graph an absolute value, we want to talk about just how to graph the parent function and then how to graph when they're changed. So first I'm going to put this on the whiteboard so I can actually draw something. So what is the shape of an absolute value function? It's a V shape, right? Pretty simple, it's just a V shape. And a V shape, the parent function V shape, which I'm going to draw on my board and you'll draw too. A little bit. You want a ruler? No, I'm okay, thank you. So, I'm just going to erase that. All right, there we go. So, we want to do a parent function first. So your parent function, there we go. Let's just draw the parent function first. If you want to do a parent function of the absolute value graph, f of x equals the absolute value of x, it is a V shape that starts in the origin, and your slope is up one, right one, up one, right one, up one, right. So everybody start by just drawing dots. Up one, right one, 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 up one, right one. And then you turn around and go in the other direction. Up on the left one, 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 up on the left one. And the fact is, if all you drew is dots, I would give you full credit. You don't even have to connect the dots. As Lee suggested, you could take out a ruler and make it look really nice. But the fact is, I know you know where those dots are supposed to be. So you don't even have to trace them. Right? Because the dots are what matter. They're telling you some specific coordinates of input-output. Okay, so we have that. And of course, I will connect it by a line. So there's my parent function. This is my parent. F of x equals absolute value of x. So now what do we want to draw on this particular graph? They want us to do f of x plus 1. So what transformation is that? If you add 1 outside, say it again?
Up one.
Yeah, just up 1. So you're just going to take your vertex of the V shape, move it up 1, and then you'll do the same thing of up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, and then up 1, left 1, up 1, left 1, up 1, left 1, left 1, and then you have your transformed function. So my blue one now is f of x plus 1. Yep. So going forward, we don't have to keep drawing the parent graph. What is this transformation? You're subtracting 2 inside the function. Exactly right. You're inside the function now, so it's horizontal, and since it's a minus 2, it's really right 2. So now you'll just go from the origin, go right 2, and that's the beginning of your V shape, your absolute value graph. So you go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, up 1, left 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 1. And then once you have all your dots, you go again. This third graph is the most exciting one. Because the 2, we've already learned represents something. What does the 2 represent? It's a stretch or a compression. So this graph is going to be twice as tall. However, there's another interpretation, which is very, very important, and I hope you add it to your formula. That k value is a representation of the idea of slope. Especially when we're talking about a linear graph. This one is linear, it's straight lines. So when there's a 2 right there, that's really 2 over 1. And if you recall our definition of slope, that slope is the up, down, the right, left. Then what we have here is telling us how to make the V. So this is up 2, right 1. So I'm going to start at the origin again, and now I'm going to go up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1. It's important that you do that. Up 2, right 1. And then you're going to go up 2, left 1, up 2, left 1, up 2, left 1, up 2, left 1, up 2, left 1. You can't have fun. We're lost. Okay, so there we go. So I got all my dots in there. I used the correct slope, and now I connect them all with a line. And you can tell now that indeed my absolute value is taller than the previous one. And you might say, what about it is taller? And what you would do is compare each individual dot. If you look at the first dot to the right, well, this one is only 1 unit tall, but this dot is 2 units tall. And so indeed, that dot is 2 times as tall as that dot. And if you look at the next dot, this dot is only 2 units tall, and this one's 4 units tall. That's twice as tall as that dot. So each individual respective dot is, in fact, twice as tall as the previous original parent dot. How does everyone feel about that? All right. Well, this is the idea of graph transformations. Philosophically, what I think is so interesting about the idea of graph transformations. Let's see. There we go. The interesting idea here is that if I go to Desmos, and I'm now going to graph a whole bunch of absolute value graphs. So I'm going to do absolute value of x, there it is, and then I'll do 2 absolute value of x minus 3 plus 4, and then I'll do negative 3 absolute value of x plus 1, and then minus 2. And you look at my graph here, what do you see on my graph? You could say I see 3 different absolute value functions, right? But philosophically, what you have here is really just one absolute value function. There's only one absolute value function. And all I've done is just pulled on it and stretched it and moved it around. It's really fundamentally the same function every time. All I've done is move it. So there's really just one absolute value function. And depending on how you manipulate it in this way, you can make it look like all sorts of different V structures. Is that fair? So the parent function is really all there is. And you just move it around. Okay, well folks, very exciting. We're all done with chapter 1. So before we move on from chapter 1, what would you like to say or do, or share your thoughts or feelings, or?
Wasn't bad.
Wasn't bad? Okay, well that's good. It wasn't too painful. Anyone else? Rubble-a-dub-dub? What'd you say? Sure.
Oh, man.
Now, here's something I'd like to say. Chapter 1 was all about functions. How does a function work?
There is a regulation. How that way so you've seen with more.
Oh, and just a couple times. Is that what it says?
Yeah.
Okay, so chapter 1 was all about functions. How do functions work? And that's essentially what we just covered, right? Like a function is an input-output machine. And what we've seen is that you can't input anything you want. You know, some inputs will lead to a calculator error. We've also seen that by using this function machine input-output, you can find certain unique points on a graph, like where it crosses the y-axis or where it crosses the x-axis. And we've also seen that with a function, you either plug things in or set it equal to something. And then finally, we are always asking the question, what does a function look like? As in, if you graph it, what does the graph look like? And then finally, we've seen that we can manipulate a function in very specific rule-based ways to make your graph look like whatever you want it to look like. Okay, so those are all the main things we've done. So what we're about to do by shifting into chapter 2, everybody, I want you to look here real closely. What we're about to do by moving into chapter 2, 3, 4, 5, 6, 8, 9, is we're about to really focus in on this. We're now about to start marching our way through various types of classic functions, like a quadratic, x squared, or a square root, and setting them all equal to 0 and solving for x. Okay? So as we do that, there's this idea that we're going to start solving for x. Let me just go ahead and talk about chapter 2 real quick to give you a bird's eye view. In chapter 2, we talk about 2 different types of functions. One of them is the absolute value function, and then the other one is the square function. Okay, this is how we're going to spend all of our time in chapter 2. We're going to look at these 2 different types of graph. What does the absolute value graph look like? A V. And what does a parabola or quadratic look like? A U. Now, I think we'd all agree that basically these 2 shapes are somewhat similar. You know, they're either like this or like this, right? One's straight, one's curvy. But they have the same fundamental attribute, which is a vertex, that is a point down at the bottom in the center. And the other main thing that they have as a commonality is the number of x-intercepts they can have. So how many x-intercepts can an absolute value graph have? How many x-intercepts can an absolute value graph have? Infinitely many? It could have 2, right? There's 2 x-intercepts. It could have 1, and it could have none. Right? So you could have 2 x-intercepts, you could have 1 x-intercept, you could have no x-intercepts. What about a parabola? How many x-intercepts can a parabola have? 2, 1, and none. Right? So this is why probably these 2 functions are studied together, is because they have similar solutions. Now, what does this mean anyway, a solution? What we're looking at here is that if I take an absolute value function and set it equal to 0 and solve using algebra, okay, so I'm going to solve using algebra, how many solutions should I get? 2, 1, or 0. So any given absolute value function, when I set it equal to 0 and do algebra, I should expect to get 2 solutions, 1 solution, or no solutions. What about a quadratic? What if I take a function that has an x squared term in it and set it equal to 0? How many solutions should I get? Yeah, 2, 1, or 0, right? So as I do my algebraic process, from the big picture perspective, I know that I can expect to either get 2 answers for x, 1 answer for x, or no answers for x. So again, when you do algebra and you solve for x, you end up with some answer, right? Like x equals 2 and negative 5, right? Or you end up with some answer, like x equals 1 or negative 3. What do those numbers even represent? Points where? They do represent coordinates, that's true. But even more specifically, any time at all that you do algebra, like let me do a simple one. X squared minus 4 equals 0. I'm going to do some algebra. I add the 4 over, I add the 4 over, I get x squared equals 4. I do square root on both sides, and because I do the square root on both sides, it's plus or minus. And so my answer is x equals 2 and negative 2. What are those two numbers? They're solutions. They're also x-intercepts. That's the big idea, is that every time you do algebra and you solve for x, quote unquote, like this whole phrase, solve for x, what did you really just find? X-intercepts. Now this is amazingly powerful, okay? Because what that tells us is that any time at all that you set a function equal to 0 and you do algebra and you get numbers, what are those numbers? X-intercepts, right? So, key big idea. Anytime you use algebra to, quote unquote, solve for x, that thing you've been asked to do your whole life, your solutions are what? X-intercepts. Now, what does that mean about you and how you can approach mathematics now for the rest of your life? Somebody walks up to you and they say, hey, here's an equation. I want you to use algebra to solve it. What could you do first? Before you sit there and start doing algebra, what could you do? You just graph it, right? You could be like, give me a minute. And then you walk over to your graphing calculator at TI-82 and you go ahead and just type in x squared minus 4. And then you say, oh, okay, well, I mean, I can tell you right now the solutions are 2 and negative 2. But now let me go ahead and do the algebra. And I'll show you the algebraic steps to support that answer. So anytime you use algebra to solve for x, whatever your solutions are, those are the x-intercepts of the graph. Which graph? The graph that you'd get if you set that equal to 0. Big deal. It has to be take a function, set it equal to 0. This is really exciting. This means that any equation you can solve with algebra, you can solve it by just looking at the graph. Now, of course, on a test, can you just use your calculator and look at the graph and then write down, hey, Mr. G, the answer is x equals 3 and 4? No. I'll give you no credit. Whereas, at least now you know what the answer is. So that when you start doing the algebra, if you get to the answer of 3 and 4, you're like, oh, good, I did it right. But if you get to the answer 7 and 9, you're like, oh, I made a mistake somewhere. Then you go back, you find your mistake, and you fix it. And you basically tweak your algebra until you get to the answer that you know it's supposed to be. Okay, so graphing calculators are not just a requirement in this course because, like, I'm telling you, you need one. It's a requirement because for the rest of your life, you know that you can use a graphing calculator to find the answer ahead of time. And finding the answer ahead of time is very helpful. Okay, so I think that's our big picture now. All right, so you kind of now see where we're going in chapter 2 and every other chapter that we do. We're going to look at a whole bunch of functions. We're going to set them all equal to 0. We're going to learn a whole bunch of algebraic techniques to solve for x, which we can then verify by using our graphing calculator. And I think I've already said that to you, that everything we do in here, you could just find the answer on a calculator, but you have to learn how to do it by hand. You know you could just look it up on a calculator, right? Okay, well, so let's take a look at chapter 2. Do you have any questions right now? Do you all feel like you know where we're heading? Yeah, we're taking a bunch of functions, set them equal to 0, solving with algebra. So the whole rest of the course is algebra, but we get to use our graphing calculators to kind of check our work. Okay, everybody, with great satisfaction, you can go to cross out 5 and 6. Now, we're going to start with absolute value functions. Again, everybody already knows what an absolute value function looks like, a phi. You know how many algebraic solutions we could have, 2, 1, or none. So already just looking at those 4 equations, I could just look at them and say, I'm either going to have 2 answers or 1 answer or no answers, right? So absolute value, let's just review, because what do most people say an absolute value function means? Like if I write down the absolute value of 5, what's the answer? And what's the absolute value of negative 5? Yeah, and so most people will tell you that what does an absolute value function do? Yeah, very good. It turns negative numbers positive, right? It turns any number positive. The only problem with stating it that way is that it's incorrect, right? So, what's that?
It's how far it is from 0.
Right, it's how far it is from 0, exactly right. So when I look at a number line, now see, this becomes immediately obvious. If I say, how far away from 0 is the number 5? 5 units. How far away from 0 is the number negative 5? 5 units. Nobody turned any negative into any positive. I asked a question. I said, how far away is it from 0? And the answer is 5 either way, because it is. Not because somebody like, turned a negative into a plus, right? So furthermore, the big mistake I see is that people take something like the absolute value of x minus 2, and they're like, x plus 2. Totally wrong, right? Because absolute value function is not some magical negative positive negative, right? Okay, so then what really is absolute value? It's just distance from 0. Distance from 0. So first of all, everybody just somewhere up at the top, write down that absolute value. So absolute value of x means distance from 0. Literal, normal, distance from 0. You're on a number line. You have to walk from 0 to that number. How far did you walk? And so I'd like to show you a visual understanding of these first 2 questions, number 1 and number 2. And that is, let's consider number 1 now. The question says, the absolute value of 3x minus 1 is 10. So what does that mean? I'm just going to cover this up with my hand real quick. Okay? What this says is, whatever number is under my hand, its distance from 0 is 10. Okay, so whatever's underneath my hand is 10 units away from 0. Well, how can you be 10 units away from 0? Where could you be? Yeah, I mean, you only have 2 options. You can either be a positive 10 or a negative 10, right? So whatever's under my hand had better be equal to either 10 or it had better be equal to negative 10. What's under my hand? 3x minus 1. So 3x minus 1 has either better be equal to negative 10 or 3x minus 1 had better be equal to positive 10. And what I'm really saying is that this number, 3x minus 1, I'm saying that's a number on the number line, and it's located at 10 or negative 10. So what does this allow us to do? To set up 2 different equations. We're either saying 3x minus 1 is equal to negative 10, or we're saying 3x minus 1 is equal to positive 10.
But 3x being, your x being the variable negative 3. Your x is negative 3.
What if x is negative 3?
Yes, what if x is negative 3?
Right, that would be one solution, because 3 times negative 3 is negative 9, and negative 9 minus 1 is negative 10. So x equals negative 3 is one solution. Yeah, that's definitely one answer. And in fact, let's just peek. Because remember, you can always peek at the answer. Let's just go ahead and graph. Now remember, in order to plug this into a graphing calculator, it has to be a whole thing equals 0. So how do I rearrange? How do I rearrange 3x minus 1 equals 10 into something that says equals 0? What do I have to do to my 10? I have to bring it over to the left. So it's really absolute value 3x minus 1, absolute value minus 10 equals 0. As soon as you have something equaling 0, that's what you type into your graphing calculator. So on my graphing calculator, I will go ahead and place in abs 3x minus 1 minus 10. And there's the first solution that Hector predicted, negative 3. The other solution is a little bit more of a bummer. It's 3.666666666 forever, right? So visually, we just saw what the 2 answers are, negative 3 and 3 2/3. But now let's finish the algebra. So to finish the algebra, we just solve these 2 equations. So I'm going to move the 1 over. That gives me 3x equals negative 9. Divide the 3 on. And we get x equals negative 3, which is the solution Hector said. On the other hand, over here now, I'm going to add my 1 over. That gives me 3x equals 11. Then I divide off the 3. And I get x equals 11/3, which is 3 2/3, which is really 3.66666 So the algebra led us to this 2 solutions that the graphing calculator showed us, which of course is going to always be true. Also, the fact that we have 2 solutions makes a lot of sense, because with an absolute value graph, the most common situation is going to be that you have 2 solutions. Unless, of course, the absolute value graph is exactly sitting on the x-axis, or if it's floating up above. We'll do number 2 and then we'll take a break. How does everyone feel about that one? I think the number line is really helpful. And don't write this down, but just maybe you remember this from your childhood. The rule that I remember memorizing when I was a kid is my teacher said, take what's in here and set it equal to that number, and then set it equal to the opposite of that number. Does anyone remember learning that from your teacher? Right, it was just this procedure. They said, hey, just drop the absolute value symbol, and then set it equal to that number, and then also set it equal to the opposite of that number. And that's the procedure. Yeah, that's true. It's absolutely true. That will always set you up to do the correct thing. You drop the absolute value symbol, and then you keep the number, and then you change the sign. Those are the two equations you set up. But I think it's way more valuable to understand what we're talking about, which is that whatever's underneath here had better be 10 units away from 0. And the only places that are 10 units away from 0 are 10 and negative 10. And therefore, 3x minus 1 has to be equal to either of those. So this gives you the reason for why maybe at one point you learn the procedure that I just said. I'm going to try this ragged Lee brought me. Ooh la la, that worked nicely. All right, that worked nicely. That worked nice, Lee. All right, number 2 then. Now, in order to do this whole strategy, the step 1, okay, is you have to isolate the absolute value. Which sounds really mean. Isolate the absolute value. It's not nice to isolate a friend. I think that sounds mean.
Assuming he's your friend.
Right, yeah, that's true. Whereas to isolate the absolute value, that's the first step. So what that means is to get the absolute value by itself on one side of the equation. So this problem starts off with 2 times the absolute value of 5x plus 1. Minus 3 equals 0. And so what I'd like us to focus on is just this object, the absolute value. This object is being multiplied by 2 and subtracted by 3. Right? So this object is being multiplied by 2 and subtracted by 3. So what's the first thing I do? Add the 3 over, get rid of it. So now I have this object, absolute value of 5x plus 1, and it's being multiplied by 2. So we divide by the 2. And now we have successfully isolated, in a nice way, this absolute value. Now 3 halves, you could write 3 halves, or you could write 1.5. I think I'm going to write 1.5. A general rule in math is that if you can convert a fraction into a nice decimal, do it. 1.5 is pretty nice. Whereas if it's the decimal 3.66666, probably just leave it as a fraction. Okay, so now what do we do? Same thing. I'm going to demo the same idea. Whatever's under my hand, where is it located? How far away from 0? 1.5 units away from 0, which is either at positive 1.5 or at negative 1.5. Those are the only 2 options. So this number, 5x plus 1, had better be equal to 1.5, or it had better be equal to negative 1.5. And this little number line that I just drew walked me through the logical chain of reasoning to understand why I'm going to write down the equation 5x plus 1 equals negative 1.5, and 5x plus 1 equals positive 1.5. You'll notice that the old standby procedure, drop the absolute value symbols and set it equal to the number, and then set it equal to the negative number, that still works. The procedure, as a rule, works. That I would be so much happier if you all understood why we were just splitting it into 2 different equations and solving them.
And what about one accent from the model class?
You just have to work on it until you get it. You can make up any equation. Any accent will do. All right, so I'm going to finish my work down here, and then we'll take a break. So now we're just doing some simple algebra. And notice, this is the simplest algebra that you can have. It's just a 1-variable algebra equation. So the first one, I subtract 1 from both sides. That gives me 5x equals negative 2.5. Then if I divide both sides by 5, that gives me x equals 1/2, or 0.5. Whereas over here, if I subtract 1 from both sides, that gives me 5x equals 0.5. If I divide both sides by 5, then I have 0.1. Now, of course,
What if you multiply by a fraction? I mean, not by a fraction, by a decimal.
what if you do? What if,
I'm just trying, you already need to add one, so I guess you just multiply by a decimal.
for which part of the step?
When you're doing it, I'm kind of like looking backwards.
Tell me more.
Well, it's the same way where I guessed 2 was -3.
Oh, okay, you're trying to work backwards?
Yeah, I'm trying to work backwards.
Well, I tell you what, trying to work backwards is a fun mental exercise, but to get all the credit on the test, you'll need to go in this forward direction, first of all. But if you're trying to figure out going backwards, I'm not even sure. I mean, what are you trying to do? Oh, you're saying,
I was trying to multiply by a decimal.
right, so 5 times 0.1 would be 0.5, and 0.5 plus 1 is 1.5. So 0.1 would work. Yeah. Okay, now, also folks, how could I have known all these answers? I could have graphed it right up front, right? So I'm going to take it, and notice it's already set equal to 0. Remember, you're only allowed to graph it if it's set equal to 0. So I'm going to take my graph, and I'm going to plug in 2, absolute value of 5x plus 1. What was it, -3? Yeah, so there's my graph, and let's just check my x-intercepts. I have an x-intercept at 0.5, negative 0.5, and an x-intercept at 0.1. So obviously, for the rest of your life, you just want to have a graphing calculator by your bed, right? I mean, there's no need to go through life doing algebra when you can just type graphs in and look at them. What else do I want to say about this? I guess that's it. Let's take a break. The time is 1:36. Let's all be back at 1:46. So Hector, you were saying, what if you multiply by decimal? You mean in the original equation?
Yes.
Right, so I mean 5 times 0.1, you could type it in your calculator, it's 0.5. Is that answer your question?
Yeah.
Oh, okay.
It's not. It doesn't answer my question. It doesn't happen. I'm just thinking about what I was trying to mental math.
Oh, yeah, like, oh, boy, in order to make that work, you'd have to multiply by a decimal.
Yes.
Okay, I see.
Yeah, I like the rags better. I like those rags.
Yeah, I gotta tell you, so far this is working very nicely. I think I like it a lot. I mean, so many erasers are terrible. Lee, how can I be in my 10th year of teaching and only just now see that obviously a rag is better? We've changed my whole, I mean, just look at how clean this is. I could even make the rest of the board look clean. Oh my gosh.
I heard of a comedian named by the name of John Mulaney.
I don't know.
But you know? No. Oh, he's on Netflix.
Really good.
Well,
I
it
think
sounds
so.
like a fictional character.
John
but-
Mulaney.
Yeah.
Basically, if you think about those like old 50s radio hosts, he has that kind of voice. He's like, well, I guess I could just look at my phone and show you real quick if you just want to take a look at it if you're interested.
Yeah, see, the eraser would not be getting it this clean.
Much nicer, right?
You know what? You should turn that into a rag doll.
Yeah, that'd be nice.
We also have a green one, but I don't think that one works as nicely as the blue one.
I was looking at the. I was going to show you guys John Mulaney if you're interested. He's just a stand-up comedian. That's it. Oh, I've probably heard of him. He's on Netflix right now. I watch a lot of comedians when I eat dinner. I like who? Honestly, I don't even know who they are. I just pop something in and then I look for more of them. There's this one guy, an older guy called Sebastian. I don't know his last name, but he's pretty funny.
My dad really likes Dave Chappelle. You know?
Yeah.
I really like Gabriel Iglesias. Sometimes Jeff Dunham. It just says some of those puppets are really creepy.
I like that.
I do.
Thank you, Dana Fonda.
I brought this for nothing. Yeah. One of those small compact ones.
Do you think you would rain?
I was planning on it, so that's what I heard in the news. But it rained like in that like really early in the morning.
I can't remember where it's from, but it's like, what I probably shouldn't say. It's like, two things that you never forget is, umbrella and,
I hear
It's a movie or show.
I know what you're talking about.
Because you never know.
It's from the movie Do Over.
Is it?
Yes.
Yeah.
I was like, because you never know when you're gonna be.
Even if I split just for a little bit.
Got
Yeah, do a chef.
Adam Sandler and David Spade.
Yeah, I love that movie.
I know that's a good movie. Especially when he comes back and he just starts spraying them with water.
Alright.
Like I think he comes back and
Sounds like a
paint.
zombie, yeah.
Oh, what was your favorite part from the
The
whole movie?
whole movie, I don't know. I think that's so hard to say just because, like, I think the beginning are just like literally. I think the part where he's like, yeah, he's like, we're gonna have the best time of our lives. Nothing was, and then he's like, they're like fishing or whatever. He gets the fish.
Oh, that part.
I just walked into some other
My favorite part is the pool scene.
Nice.
Oh yeah.
Yeah, where the basically like, I'm gonna get you, like, get shot at me.
It's shot 3 times.
And you have like the world's tallest gymnastics.
Yeah.
Hey, it's cool as in my dad's trip. It's cool as in my dad's trip. Yeah. All right, folks, it's 1:46. Let's keep going. So what we see on the board here are different graphs that we can graph. And I think in order to do this, before we do that, let's just wrap up this idea. Okay, so we just finished solving number 2, and we got down to the idea that the answer is 0.5 and 0.1. No, sorry, negative 0.5. Wasn't that a negative? I dropped my negative a long time ago. That was negative 2.5, negative 0.5, negative 0.5. Okay. So when we say that these two numbers are the solutions, what do we mean?
Yes, the other
X-intercept, right? Okay, so let's look at our big point here, our big idea. How do you know that your solve for X solution is correct? So as you go through this class, you're going to do a lot of algebra. You're going to solve for X a whole bunch of times. How do you know that your solution from solving for x is actually correct. And one way to know is to just graph it, right? And look at the x-intercepts. So provided you graph it and the x-intercepts are the same as your solution, you know that you're correct. But there's one other very important idea that we're going to come back to over and over again. How do I know that these answers are correct? Exactly right. You just plug them in. So like, look right here. I'm going to plug in 2 times 5 times negative a half plus 1 minus 3. So 5 times negative a half is negative 2.5. Negative 2.5 plus 1 is negative 1.5. So now I have 2 times negative 1.5 minus 3. 2 times, well, the absolute value of negative 1.5 is positive 1.5. So 2 times 1.5 minus 3. 2 times 1.5 is 3, and 3 minus 3 is 0. So it's true. If you plug in the number, it should make the original equation true. Try that again. Here I'm going to plug in 0.1. So 5 times 0.1 plus 1, absolute value minus 3. 5 times 0.1 is 0.5. 0.5 plus 1 is 1.5. So I have 2 times the absolute value of 1.5 minus 3. Absolute value of 1.5 is 1.5. So 2 times 1.5 is 3. And again, 3 minus 3 is 0, and it's true. So that's actually the more important definition. That how do you know that your solutions are correct? Plug in to original equation, the original equation which you graphed, and make sure it's true. Okay. This is wonderful. Okay, we have at your disposal 2 different methods to check to make sure that your answer is correct. Right? Because here's the thing, a lot of times a student will finish a test and then they'll turn it in and they'll say, I wonder if my answers are right. I mean, is there any reason to turn in a test without knowing whether or not your answers are right? There's absolutely no reason, right? You can either plug it into the equation and see that it's true, or you can just graph it on your graphing calculator. So, I mean, you should know ahead of time which answers you got right and which answers you got wrong, because you can grade the test yourself. Okay, so we're going to come back to that theme over and over, is knowing if your answers are correct. So now, let's do a couple more graphing examples. Now, I'll just plug this up. And now I need to turn on that screen again. Oh, that's already.
I've actually wanted to ask about this a while. How do you put that figure inside your graphing calculator?
I will tell you. Which figure?
Just basically a line.
Oh, the absolute value.
Absolute,
Yeah, absolute value. If you're on Desmos, you just type in AVS and it becomes the absolute value. But in your TI-80 calculator, you go to Math, the button Math,
Okay.
and you go over to the option called Number. And then it's the very first one, AVS.
Oh, okay.
That's not your abs, right? That's absolute value. So it's under Math, and then you go to the right, and it's under Number, and it's abs. So there it is.
So it would be the first one just like X.
Oh, you want to try plugging it in?
Yeah.
Sure. If you were to go into your TI calculator now, well, first of all, you'd have to be in the Y equals screen, first of all. So, okay, so you're in Y equals. Then you hit Math, and you go to the right, and then abs is there. Just hit Enter. And now it says abs. So like for this first one, it'd be abs. And then you type X plus 4, and then you're ready to graph it. You know, at some point, we should just do some examples on our calculators.
Yeah, because this is all that we're going to be able to use on our test, right?
Yeah. Yeah, so I'll give you some instructions. Let's do them by hand first, and then we can go back and talk about how to plug them all in.
Okay. So every time you have an equation, you have an answer math.
Yeah, I mean, to get
Everything.
by hand. Yeah. Anything that I grade, your test, your homework, your practice test, it all has to be done on paper anyway. The graphing calculator is just to verify that what you have is correct.
Mine doesn't come up.
It doesn't.
It doesn't
Let's,
graph it.
but that's just, you have something else going on, like, let's see, that's fine. Invalid domain, what'd you type in? Abs X plus 4. You've got something else going on up here with the plot 1. So, oh, and I just turned it off, so now you should be fine.
Thank you.
Sure. Okay, so folks, let's try this by hand first. So our first graph is the absolute value of X plus 4. So first of all, what transformation is that? The plus 4 is inside the function. So there's really left 4. So let's try it out. We're just going to go from the origin left 4, and then you draw a V. Now, the thing I ask is, don't just draw a V like, that's very unprofessional. All right, at the very least, like I said, I just want to see dots. If you just draw dots, I'm happy. So up one, right one, 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 and then up one, left one, up one, left one, up one, left one, up one, left one, up one, left one. I would accept that any day. I would give full credit for this. So while you don't even have to trace it, what I want to do is actively discourage anyone from just, like drawing some slashes, because that's not accurate at all. Okay, how about this next one? The plus 4 is outside the function. So what does that mean? Up 4. So from the origin, you go up 1, 2, 3, 4. And again, you draw up one, right one, up one, right one, up one, right one. And then up one, left one, up one, left one, up one, left one. And yeah, theoretically, you're always supposed to go until you get to the edge of the graph. So you would keep on making dots all the way until you fall off the edge of the graph, and then you'd say, I'm done. There's my graph. Again, that's full credit. If you draw that, I give you full credit. I don't even care if you draw it. Okay, next one. You'll notice that the 4 is inside the function. We didn't talk about that, but I want to teach you something here that, you know how you can factor out a number? Like let's say you had 4x plus 8. What can I factor out?
4.
Yeah, I can factor out a 4, so that leaves behind x plus 2. Or if I wanted to, I could just pull out a 2, and then I would leave behind 2x plus 4. Right, so the whole idea is that you can factor, and this is what we're going to review in chapter 2. So you can factor a single number out of an absolute value. So I can rewrite this now as 4 times the absolute value of x. So now that the 4 is outside, what does it represent? It's a vertical stretch, so it's 4 times as tall. And more importantly, it represents a slope. So we're going to start at the origin, and now the slope is 4 over 1. And remember, slope is the up, down, over the right, left. And so what we're really saying here is that the slope is up 4, right 1. So from the origin, you'll go up 4, right 1, up 4, right 1, up 4, right 1, fall off the graph. And then you'll go up 4, left 1, up 4, left 1, up 4, left 1, fall off the graph. And then you can trace it in with a line or not. So I'd give you credit either way, so long as you have the dots. So how about this one? There are 2 things happening here. If we have the absolute value, what 2 things are happening?
Can I say in terms of I have 3 negative there?
Sure.
I have put -3.
Yeah.
And then put abs, and then put max, and enclose the first parentheses.
Correct. Now, what are the 2 transformations? What does the 3 represent?
Stretch.
It's a stretch, which means the slope is 3 over 1, up 3, right 1, up 3, right 1. But there's a minus sign, which actually means that the V is upside down.
I don't believe you.
You don't?
Yeah, because it's stretch.
Right, right. But remember my original equation, which I've now erased, was you have a plus or minus out front, which means flip, the first value, which meant a stretch, and then you have your function where the inside is right and left, and then the outside is right, up and down. So this right here just says flip it upside down and right side up. And this K is how much to stretch it. And plus, you don't have to believe me. You can type it into a calculator and see that it's upside down. So this is still a regular function starting at the origin. We are going to do a slope of 3 over 1, but it's going to be upside down. So now you would count it as down 3, right 1, down 3, right 1, down 3, right 1, or down 3, left 1, down 3, left 1, down 3, left 1. And again, whether you connect the dots or not, that's what the absolute value of that looks like. And actually, now that you know how to graph it, you should go ahead and type it in and make sure that it's upside down. Oh, good. Okay.
The reason why I didn't believe it because it was a stretch.
Oh, yeah. It is both. Yeah, yeah. So that's 2 pieces of information. The 3 is the stretch. The negative means it's upside down. Okay, how about the next one? We have now 3 pieces of information. And so it's important to be able to say all 3 of them separately. Is that a -4?
Yes.
Yeah, -4. So, I can just move that down. So, now what? What are the 3 pieces of information? What does the -4 outside mean? Down 4. And what does the +4 inside mean? Left 4. What does the 3 outside mean? Yeah, 3 over 1 is our slope. So we start with the origin. We go down 4, left 4. That's not the slope. That's just our starting point. Now our slope is up 3, right 1, up 3, right 1. So we go up 3, right 1, up 3, right 1, up 3, right 1, up 3, right 1. Or up 3, left 1, up 3, left 1, up 3, left 1, up 3, left 1. You notice right now we're responding to the question, what does that function look like? Right? We are our own graphing calculators. Somebody writes this down, you can look at it and say, oh, I know what that looks like. It looks like that. And everyone can cross out number 6. That is good. And that's it with section 2.2. So everyone can just cross out number 6. We're all done with absolute values. We've seen how to solve an absolute value equation, and we've seen how to graph an absolute value equation, how to graph the slope, how to graph a transformation. So you can basically say you're really good at absolute values now.
I have a quick question.
Yeah.
I know we're not going to do 6, but we would just, what we're trying to do is get rid of like we did in number 3.
So in this one, I can show you real quick. First of all, the 2, anytime you have a number on x, you got to factor it out, just like we factored out the 4. So what we really have here is 1/3 absolute value of 2 outside of x minus a half. But we want to bring that 2 outside, so then the 2 would come outside and be 1/3 times 2 absolute value of x minus a half. Because inside you want the x to be by itself. I'm giving a lot of information right now that you're not going to need. It won't be on the test. And then 1/3 times 2 is really 2/3, so that's really just my slope. So that's the actual thing that gets graphed. See, what they're really doing right here is testing to see whether or not you know how to factor out the 2. So once you do factor out the 2, you start by moving right a half, which this is very difficult to graph because you're halfway through a grid point. And then the slope is up 2, right 3. So just think, you got to be halfway through the grid point and then go up 2, right 1, 2, 3, up 2, right 1, 2, 3, up 2, right 1, 2, 3, and so on.
You get the negative half just from dividing.
By factoring out the 2.
2, yeah. Okay.
Yeah. And then you go the other way, up 2, left 1, 2, 3, up 2, left 1, 2, 3, and so on.
Okay.
Yeah.
Thank you.
You're welcome. Okay. So now we get to move on to quadratics. Quadratics are like absolute values, but they're curvy. Right? So a parabola curves, whereas an absolute value function is just straight. That certainly makes an absolute value function easier to graph. Because if you went to go graph a parabola, the natural question to ask is, how curvy should I make it? Right? I mean, if you're going to graph a parabola, do you do it like that, or you do it like that, or you do it like that, or you do it like that? I mean, that leaves a lot of wiggle room to figure out, gosh, how do I be precise about this? And so, fortunately, there's a very simple answer to that. But first, let's plot what?
Plot the points.
Well, yeah, you could always just plot the points, and that's how I was raised, is I would just plot the points. And then somebody taught me a better way. And I was like, oh my gosh, I can't believe I lived my whole life plotting points. Okay. So this whole page, what you see here, is just a reference sheet. I don't want you to feel stressed out by it, like, oh no, I have to understand everything on this page. Rather, I just want you to know that, hey, here's a list of equations, and you can always come back and reference it. So the first thing I want you to look at is the very top equation, ax squared plus bx plus c. I bet you all recognize that general form. So when I say f of x equals ax squared plus bx plus c, that's the general formula for a quadratic, and the a, b, c go where? Into the quadratic formula, right? So that's, these two things go hand in hand. If you're given a quadratic in this form, that means you're about to probably choose the quadratic formula. Whereas look right below it, you've got standard or vertex form. Look at how that's written. F of x equals a times x minus h squared plus k. What's this?
That's not.
Yeah, this is the transformation form that we've just been working on. This is outside, so it's up and down. This is inside, so it's right and left. And that's the stretch compression factor. So that's nice. Okay, so on the one hand, we have this general form that you can use the quadratic formula on. Or you have the transformation form that will immediately tell you how to graph it. Like immediately, like bam. I know I go up that far, right or left that far, and I give it that slope. Okay, so they tell us something else up there. They tell us the vertex. So there's the vertex formula. They tell us a lot of things. The axis of symmetry, the domain, a lot of information. And I'm not going to just sit here and read through this with you because you can always sit down and read through it on your own. We're just going to encounter it as we go. So just know that this whole page is just reference information. It's there for you. So let's try it. If you turn the page, the very first set of problems is just to graph, right? And so we immediately have this question, well, how do I graph it? How do I graph a parabola because it's curvy? I want to make it the right kind of curvy. Oh, man, I need to graph it on the board. I need a better system. There's that. There's that. There's that. All right. Okay, so we're going to graph these. Now, there's a whole bunch of instructions up there. We're just going to graph it. So, let's just do it in terms of transformations. What is the transformation on the first graph?
It's like the left.
There's the +2 inside. So what does that mean? Yeah, left 2. So I'm going to write that, L2. And then there's a negative sign out front, which means flip it upside down. So I'm just going to write flip. Okay. All right, well, that's all good. We have to do that. Let's first draw the parent graph. Okay, let's just talk about the parent graph. How do you draw a parabola? Well, we know that a parabola, the parent function, is just f of x equals x squared. And it's centered at the origin. So that's like your pin the tail on the donkey point. And now we want to draw a parabola. Well, how do we draw the right parabola? There's a rule that I want to teach you, and it's called the 1-3-5 rule. And I didn't hear about this until after high school, probably even after college, and then somebody told it to me, and I was like, so how do I graph this? This 1-3-5 rule, first of all, those are just the odd numbers, 1, 3, 5, 7, 9, 11. Keep going, odd numbers. These represent the changing slope of my graph as I move away from that vertex. So this is really up 1, right 1, up 3, right 1, up 5, right 1. These are slopes. So starting from the vertex, I'm going to go up 1, right 1, up 3, right 1, up 5, right 1, up 7, right 1, and so on. I never thought about that. It's fantastic.
Right.
Okay, then I'm going to turn around and go to the left. So I'll go up 1, right 1. I'm sorry, up 1, left 1, up 3, left 1, up 5, left 1, up 7, left 1. And this exactly determines a parabola. Now, if you're like me, when you're in your childhood, you're like, okay, how do I graph this? I have to make a table of values. And you're like, oh yeah, we're plugging all these tables of values. I gotta compute all these things, and then when I'm done computing, I can plot all these coordinates, and then yeah, exactly. And that's fine. You can do that. But the 1-3-5 rule gets you there faster. So let's go ahead and try using the 1-3-5 rule to graph what they actually want us to graph. So first of all, we're going to move the vertex left 2. So I'm going to go left 2. There's my vertex. And we're going to flip it upside down. So we're going to apply the 1-3-5 rule, but going down. So what would that mean? Down 1, right 1. Down 3, right 1. Down 5, right 1. So I'm going to start here. I'm going to go down 1, right 1. Down 3, right 1. Down 5, right 1. And that's the beginning of my parabola. And then I'll turn around and go to the left. Down 1, right, I'm sorry, down 1, left 1, down 3, left 1, down 5, left 1, so on. And that's it. A little bit more consuming than an absolute value graph, because the absolute value graph had the same slope the whole way. Right? When you do an absolute value graph, you're constantly using the same slope up 3, right 1, up 3, right 1, up 3, right 1, up 3, right 1. Whereas with a parabola, you're changing your slope every single time you move. Any questions about that? Okay, number 2 is a little different because there's a 2 there, so let's move right on over to number 3. What transformation happened here? There's a +2 outside, so that means up 2. So we'll move our origin up to 2, and then we'll go, well, we didn't move the origin. I moved the vertex up to 2. And now I'll go ahead and do the 1, 3, 5 rule again. So, does it help to write it down again? I mean, maybe just to bring your consciousness to the fact we're talking about slopes. To go up 1, right 1, up 3, right 1, up 5, right 1. Really helps if you go high pitch. So then we'll go again, we'll go up 1, left 1, up 3, left 1, up 5, left 1. Now I know you're all dying to know why the 1, 3, 5 rule works, right? I knew it. So let's just make a table of values real quick, where we're doing x and x squared. We're going to do 0, 1, 2, 3, 4, 5, the x inputs. And we're going to square them all, 0, 1, 4, 9, 16, 25. And now we just ask the question, what's the difference from 0 to 1? What do you have to add? What's the difference from 1 to 4? And the difference from 4 to 9? And so on. So the difference between square numbers is the odd numbers. It keeps going forever. So the difference from 9 to 16 is +7. The difference from 16 to 25 is +9. And so, yeah, I know, crazy, right? So there's the 1, 3, 5 rule. It's fun, right?
Actually, I think I remember seeing this in the book. There was a math book. It wasn't like a story,
Oh.
but it involved like these little like tricks and tips.
Oh, well, if you find the title of that book, let me know. That sounds like a good book. Okay, so that's your number 3. Let's go back now to number 2. Number 2, we have 4 different things happening. Right? What are the 4 different things that are happening? What does the +4 mean? Yeah, up 4. So we're moving our vertex up 4. What does the +1 mean? Left 1. So we move the vertex left 1. What does the 2 mean? Yeah, 2 represents slope somehow, which we need to now talk about in light of the 1, 3, 5 rule. And then the negative means flip. So I really want you to look at that. I mean, just realize this is not something that you just do somehow in your head automatically. Like, you got to take your time and say, okay, I'm going to start at the origin. I'm going to go up 4, left 1. That's my vertex. I'm going to be flipping it upside down, so I know I should be graphing it down. So I'm going to make a little reminder here. I should look like that when I'm done. And now, what is this slope? So the 1, 3, 5 rule is actually the 1A, 3A, 5A rule, where A is the number in front of the parentheses. That was on the formula. If you look at the formula sheet, look at the top of your previous page. What's the letter in front of X? Up at the top there? A. So that number 2, it's really the 1A, 3A, 5A rule. So in this case, the letter A is 2. So really 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 10. This graph follows the 2, 6, 10 rule. So starting at my vertex now, I'm going to work downward. I'm going to go down 2, right 1, down 6, right 1, down 10, right 1. So down 2, right 1, down 6, right 1, down 10, right 1. And then I'll turn around and go to the left. Down 2, left 1, down 6, left 1, down 10, left 1. There's our upside down parabola. It indeed is steeper, right? It was a stretch. We stretched it, and it follows that way. Hector, did you write down the 1A, 3A, 5A rule? Did you write down the 1A, 3A, 5A rule? Okay, great. Okay, any questions about graphing these? So, oh yeah, Emily, go ahead. A is 2. The number out in front is 2.
Yeah.
And that means you have to take your 1, 3, 5 and multiply all of them times 2.
Oh.
So 1 times 2 is 2, 3 times 2 is 6, 5 times 2 is 7, or 10. And then the next one, 7, would be 14. You just, whatever your A value is, whatever the number is in front, your stretch factor, you multiply through by the 135. Yeah. No, thanks for asking. Thanks for clarifying. Okie doke. Well, keep in mind that graph transformations follow the same rules no matter what function you're looking at. You just move it right, left, up, down, flip it upside down, and change your vertical compression or stretch. Any questions you want to ask right now? All right, so this, a little different. This is now written in general form. And you have a lot of space on that page. So the first thing I'd like us to do is take some notes so that we understand what we're looking at. And then we'll graph. I think I'll just keep it on the board here. It's be easier to do. So put it back on the projector screen. So what I'd like us all to do first is make a formula sheet for when you have things in general form. So everyone, this can take up as much room as you like, or you can do it on a separate sheet of white paper, but doing it right here is fine. If your function is ax squared plus bx plus c, then we'd like to have a visual understanding of where the key parts of your graph are. Now this is a parabola, so what we're going to do is start by drawing a parabola. And try to spread your parabola out like I just did. So the whole thing is to the right, but it does eventually cross the y-axis. And what we're going to make is a graph, which is also a formula sheet. So first of all, what are the 3 different key things we want to label on here? We definitely want to label the x-intercepts, right? We want a formula for the x-intercepts. Now, by formula for x-intercept, I mean a lot more specific than just saying f of x equals 0. We do know that it's f of x equals 0, but I mean, we're going to get a formula for it. So, yeah, we need to understand what's the formula for our 2 x-intercepts. What else do we want? The y-intercept, we want a formula for our y-intercept. And what else do we want? The other special point on a parabola.
On the
Vertex. Okay, so we want a formula for each of those. So we might as well start with y-intercept because that's always the easiest. If you want the y-intercept, you just plug 0 into the function. If I plug 0 in, that's a times 0 squared, which is nothing. B times 0 is nothing. And that just leaves c. So the y-intercept is c. Whatever the c value is, that's your y-intercept. Okay, next, x-intercepts. We know that x-intercepts are when f of x equals 0 and solving for x. Well, the good news is we already have a formula. Don't write this down just yet. But we have the quadratic formula. Negative b equals or minus the square root of b squared minus 4ac all over 2a. Now, whenever you use this formula, how many answers does it give you? Why 2? Because the plus minus, right? So you always end up with something like 3 and, all right, like this, -5 and 3. All right, so does everyone agree that the quadratic formula typically gives you 2 answers because you have the plus or minus? Yes. When would you only get 1 answer?
if you're negative, if it was negative, then you can't figure it out. No.
Oh, you mean if these 2 cancel each other out?
Yeah.
Yeah, maybe. No, you still have 2 answers. Yeah, you need a 0 right here. Because then you're plus or minus and nothing. You know, if you're plus or minus nothing to something, you still just have the same answer, which is 1 answer. So you could have 2 answers. You could have just 1 answer. Okay? Or if that square root term was negative, you'd have no answers, because that's imaginary. So keep in mind here, we're remembering that you could have 2 solutions, you could have 1 solution, or you could have no solutions. Right? And that's basically what that looks like. Provided you have a positive number in here, you're going to be plus or minusing something, so you get 2 answers. If you have a 0 in there, you're not plusing or minusing anything, so you just have 1 answer. But if you have a negative number in there, that's imaginary, and so there's no x-intercepts. Okay? So for the moment, let's just know that that's the possible realities from the quadratic formula. You either have two answers of 1 or none. But let's focus again on that plus or minus. This is really cool. I'm hoping you've never seen this before, because you'll say, wow. This x-intercept on the right is negative b plus the square root of b squared minus 4ac over 2x. And this x-intercept over here on the left is negative b minus the square root of b squared minus 4ac over 2x. So what does that plus or minus really represent? Yeah, the x-intercept on the right and the x-intercept on the left. So that's what that plus or minus represents. It was the two values, one to the right, one to the left. So far, so good. We have the formula for the y-intercept is just c. The formula for the x-intercepts is negative b plus square root of b squared minus 4ac over 2a. And this one. And notice just how wildly, hilariously different those are. Like, how easy is the formula for the y-intercept? Painfully easy. You just have to look at that number. Whereas, what's the formula for the x-intercepts? Painfully hard, right? Because you got to sit there and do all that computation. Okay, so there's one formula left that we need. That's our vertex formula, and that was listed on the first page. You know, a page ago, if you flip and look. The vertex formula is negative b over 2a. And that's the x value of the vertex. Where does the b and a come from? Those two numbers. And then the y value you get by just plugging whatever answer you got for negative b over 2a and plugging it into the function. Because remember, this is your input, this is your output. So if I plug negative b over 2a in as my input, the output is the y value. So we say the y value is just f of negative b over 2a. Okay. So this right here that you now have drawn would be great to tattoo on your face or your neighbor's face, or put it on a t-shirt and sell it on Amazon. Make $1 million. Who wouldn't want this? So this is what we're going to practice. We're going to practice going through these computations. Now you might ask yourself, which computation do you want to do first? Like if you want to feel good about yourself, might as well do the y-intercept, right? It's super simple. And then, you know, what do you do next? It all depends on what you're in the mood for. You know, do you do the x-intercepts next? Do you do the vertex next? It's totally up to you. I'm going to go in this order because we've already been talking about solving the y-intercept and then the x-intercept, and then we're just going to tack on the vertex at the end. So let's try it for number 4.
I have a quick question.
Great.
In this case, couldn't we just find the zeros for the x-intercept by
Factoring?
Yeah.
We could, but we haven't gotten to factoring yet. Factoring is going to be chapter 2.4. This is 2.3. And in section 2.3, they want you to do these. But Omar, absolutely. You could way more easily find the x-intercepts by factoring. Of course, you could way more easily find the x-intercepts by just graphing, right? I mean, graphing, you're done. Okay, so let's go in order, folks. Number 4. Let's start with the y-intercept. The y-intercept, which is equal to f of 0, which in this case is equal to c, is simply equal to negative. Oh, by the way, I should write it down. F of x equals x squared minus 2x minus 8. And by the way, I should put a 1 on the x squared. And I'm even going to go a step further and say a equals 1, b equals negative 2, c equals negative 8. All right, just so that information pops off the page. You know, you're slapping the person in the face with it. These are your values for A, B, and C. So I got my y-intercept, that's done. X-intercepts. We're going to go ahead and solve. Now, whenever you do the quadratic formula, it's really important. Write it down once. Negative b plus or minus square root of b squared minus c over 2a. And then write it down empty. We write it down empty so you have a spot to plug in all those numbers. So what does it look like empty? You're going to replace every letter with an open parenthesis. So you might want to watch as I say it. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So you can see anytime I said a letter, I just wrote an open parenthesis. Now I can go in there with my numbers that I very specifically noted. And And I can even point now, because my formula is right on top of it, so I can say, okay, I need B, that's -2. Now I need B, that's -2. Now I need A, that's 1. Now I need C, that's -8. Now I need A, that's 1. Because if you're going to make a mistake, when are you going to make a mistake? Like, when? Yeah, like right now, right? This is the time where you want to be really careful. And all the computation you're about to do. So how much computation should you do? A little bit at a time. Just a little bit, right? So like -2, that's 2. And then on the inside of my square root, -2 squared, that's -2 times -2, that's 4. And then -4 times 1 times -8, that's a plus of 32. And then on the bottom, 2 times 1, that's 2. Now anybody in the audience is looking at 4 plus 32 and they're like, that's just 36. Why didn't you just write down 36? Well, because that would have been too much to do all at once. To say, okay, that's 4, okay, that's 32, that's 4. You could make a mistake. So you just stop there and say, okay, now I've got 2 plus or minus root 36 all over 2. And again, in the audience, they're like, what? Just wrote 36 and 6. Why'd you write it down? Because you're going slowly, taking your time. So now I can say, what's the square root of 36? 6. So now I have this. And this is where I'd like you all to know the notation I'm going to use, and I hope you use it as well. This plus or minus represents alternate realities. Well, specifically, it represents the right x-intercept and the left x-intercept. But I'm going to denote my alternate realities with arrows. I'm going to say, okay, I'm going on 1 of 2 different choose your own adventures here. One reality, it's 2 plus 6 over 2. My other reality, is 2 minus 6 over 2. So I just wrote down my 2 alternate realities. That is my right x-intercept and my left x-intercept. Now again, I just move along. 2 plus 6 is 8 over 2. 8 over 2 is 4. And then 2 minus 6, that's -4. -4 over 2, that's -2.
How many hours do we have with this?
As long as you need. All right, so what have we found out so far? We can start keeping track of our work by making a graph. We say, well, so far I know my y-intercept is -8, so I come down here to -8 and I put a dot. I know my x-intercept is at -2 and at 4. So there's my x-intercepts. And everything's looking good so far. Right? The parabola is revealing itself. So last, we do our vertex. And the vertex formula, first we find the x value of the vertex. Because remember, a vertex is a coordinate, x comma y. How many things do we have to solve for? 2. So first we solve for x. X is -b over 2a. Again, write it empty. -b over 2a. The formula for x. Now keep in mind right here, see this is very confusing. I'm writing x equals. I'm not talking about the x-intercept anymore. Now I'm talking about the x value of the vertex. I wish there was a better notation to be more clear about that. Like right up here, I said x-intercept, x equals. And I'm saying vertex, x equals. They both look like x equals, but they represent very different things. So again, my b value is -2. My a value is 1. And so the x value of my vertex is 2 over 2, which is 1. So that's the x value of my vertex. Now how do I find the y value of my vertex? The y value is f of -b over 2a. Does that mean? That means just plug that number you just got into the function, f of 1. Now, even though we're plugging in a very easy number 1, it's not always obvious how to do this computation in your head. I wouldn't try it. You could get an accident. So 1, I'm just going to go and write that empty. I've got 1 something squared minus 2 something minus 8, and I'm plugging in 1. Or you could plug it in your calculator. So this gives me 1 squared is 1 plus 1 is 1, minus 2, minus 8. So 1 minus 2 is -1, -1 minus 8 is -9. What did we just find out? The vertex is at 1, -9. What do we do with that information? Put it on our graph. And now we've got 4 really nice points, our 2 x-intercepts, our y-intercept, our vertex. And now we all know exactly how to draw our graph. Nice notes, nice highlighting too. Hey, really nice. You're looking good. Nice graph. Nice. You done as much as you can. I know that you're a little tired, but you done as much as you can. Very nice. Can you put your format somewhere else? This thing?
Yes.
Oh, good. Okay, okay, yeah, okay, good. Yeah, very nice. Okay, so you can put your graph on your grid. I just put mine on the page there. I could go over here now, though, and make a really nice one. So now my graph, again, finding all those points. My x-intercept is at -2, and 4, and my y-intercept 1, 2, 4, 5, 6, 7, 8, and my vertex was at 1, -9. There we go. Hey, here's a fun question. You know that your parabola is symmetric, left and right. Since there's a point here, where else do I know there's a point? Right there, right? Does everyone agree? That since there was a point there, I can go ahead and put that point in. It's like a bonus. Yeah. And plus that just helps me go. Okay. Now, super bonus, because you're all such sophisticated mathematicians. How do I write this parabola as a transformation? So where did my vertex go?
From 0, 0 to
Right 1 down 9, right? So right 1 would be -1. Down 9 would be down 9. And what's my original slope? Up 1, right 1? So that's the 1, 3, 5 rule, so that's a 1. Look at that. So now we know what that looks like in transformation form as well. That was just a freebie. All right. Now, we don't have to do both number 5 and number 6. And honestly, I don't want to do both of them. So how about we choose? Actually, maybe the last one would be best. Yeah, because the -3 makes it interesting. Yeah, let's do number 6. Everybody, you can cross out number 5. Plus, that gives you more space on the page, so you don't have to fill the whole thing. So I'm gonna leave that up there, all my work, just in case anybody's still looking at it. I'm gonna come over here to do number 6. So, to begin with, I hope you all do the same thing. Write down the function. f of x equals -3 x squared plus 4x minus 7. And again, just to really put it in people's faces, A is -3, B is 4, C is -7. See, the problem is that a lot of people forget the negatives. And they're like, A is 3, C is 7. No, it's not. So now, let's go in the same order. Y-intercept. As we know, the y-intercept is always equal to f of 0, which is in this case equal to c, which in this case is -7. Now you notice how I wrote y_int equals f of 0 equals c equals -7? I'm just showing the chain of reasoning. It's not like you got to write that down every time. But it's very valuable if you understand what that means. That the y-intercept is always equal to f of 0, which in the case of a quadratic is just the c term, which in this case is -7. Okay, let's do our x-intercepts. As before, you write it down first, -b plus 1. By the way, have you ever heard the song "To Pop Goes the Weasel"? You know "Pop Goes the Weasel"? It's like so it goes like this. It goes -b plus or minus square root of b squared minus 4ac all over 2a. And I really just did that to give you nightmares. So now you'll think about it later today. All right, so now I write it empty. So writing it empty. -b plus or minus square root of b squared minus 4ac all over 2a. So I've got it nice and empty now. Hey, Hector. Hector, are you with us? We're on the x-intercepts for this one.
Okay.
All right, so now let's plug everything in. Again, it's nice to have the real formula right above the empty formula because you can point at it with your fingers. I need b, I need A, I need C, and I need A. Right? Because this is the most important part. You plug those numbers in very carefully. All right. So a little bit at a time. What do we have? That's a -4 plus or minus. On the inside, I'm just going to do a little bit. 4 squared is 16. Negative times a negative times a negative is negative. And 4 times 3 is 12 times 7 is 84. All over 2 times -3. Now, you don't have to be able to do all that multiplication in your head. Well, no. Just type it in your calculator. Find out what it is. So now we have -4 plus or minus. What is 16 minus 84? The -68?
Yeah.
Well, that's a problem. Yeah, it's negative. Can you square root a negative? No. So what does that tell us about the x-intercepts? There are none. And what does that tell us the parabola looks like? It either looks like that, or it looks like this. And since it's a -3x squared, the parabola is facing down. So now we know that this is actually what our parabola is, and there are no x-intercepts. So that whole, all that work that we just did, you just say there are no x-intercepts. Okay, so now we can finish up and find our vertex. So vertex. So we know that the x value of the vertex is -b over 2a. As before, you write it empty, -b over 2a. And what numbers do we plug in? b is 4. A is -3. And that gives us -4 over -6, which is a positive, and negative over a negative is positive, 2/3. Okay, so now we have to plug 2/3 into the function. So y is going to be f of -b over 2a, which means we're plugging in f of 2/3. So what's the easiest way to plug 2/3 into our function? I mean, on the one hand, I don't think anybody in here actually wants to do -3 times 2/3 squared plus 4 times 2/3 minus 7 by hand. Nobody wants to do that by hand. So you have to type it in your calculator. Let's all be very careful about typing that in your calculator. So everyone take out your TIs, and we're going to very carefully write -3 parenthesis 2 divided by 3 parenthesis caret 2 plus 4 parenthesis 2 divided by 3 parenthesis minus 7. So this is our first little calculator lesson. What you type in should look exactly like that. The parentheses around the 2/3 are very important. Anytime you have a fraction on your calculator, you need to wrap it inside parentheses. So try typing all that in and see what you get. That sounds correct. You should end up with -5.666 repeated. Now, keep in mind that when you type your answer into the More website, you can't type in 0.6 repeating. And More wants 4 decimals of accuracy. So that would be -5.6666. Is that accurate to the 4th place? Yeah. What do we have to do to that 6? Because the next one's a 6. So you actually have to round it up to a 7. So More would only give you credit if you wrote 6667. They want you to round all of your answers to 4 decimals of accuracy. But what would be better than -5.666 repeating? Take your answer, if you still have it on your calculator. So, or you can just type in -5.6666666 and type enough 6s to fill up a whole line. And then you can hit a really wonderful button called the math button. And then the very first option says frac. So you hit enter, enter. And it's -17/3. That's an even better answer. Especially because our first part of the vertex was 2/3. Now the second part of our vertex is -17/3. And so our vertex is 2/3 -17/3. Now, this is incredibly accurate and doesn't deal with decimals or rounding or anything, and that'd be a good way to type it into More. But if you wanted to graph this yourself by hand, you'd have to say, well, 2/3 is really 0.6 or 0.67. -17/3 is really -5.6 or 5.67. So how do you graph that? I mean, that's not on a grid.
Very careful.
Yeah, very carefully would be a good answer. How do we graph that? I'm going to tell you how you graph it. So our vertex, folks, go to your second graph now. We're going to graph 0.67 down 5.67. So how you say that in English is right a bit, down 5 and a bit. So you're going to go right a bit, right? Like not even a full 1, just a bit. So you can just basically choose anywhere in the middle. A little more to the right, but right a bit, and then down 1, 2, 3, 4, 5, and a bit. So you'll see your vertex is floating in the square because you went right a bit and down 5 and a bit. And that's more than good for plotting the graph by hand. Once you have that, we don't have x-intercepts. We do have a y-intercept. Where was that y-intercept? -7. So 1, 2, 3, 4, 5, 6, 7. And now you might look at that and say, how are we supposed to graph that? You know, we don't have anything else. Except for the fact we know it's facing what, up or down? Down. It's facing down. This is the vertex. And because a parabola is symmetric, do we have a bonus point? Yeah. We do have a bonus point. Now remember, the vertex to get to that point would be left a bit down to there. So you're going to go right a bit down to there. You need to kind of plot that other point symmetrically. And there you have the tiniest, cutest parabola. And of course, if you're feeling uncertain, did I do that right? Is that really what it's supposed to look like? You'd go on over to your graphing calculator and you graph it. So -3x squared plus 4x minus 7. And there's the parabola. And yeah, that looks great. There it is, right a bit, down 5 and a bit. Y-intercept at -7. There we go. That's it. Oh, thanks. Okay, now. Okay. But yeah, about 10 minutes left. Folks, I realize that what we just did is very demanding, isn't it? It's very demanding. How would you describe what we just did? I mean, look at that problem. There's a lot of steps, right? It wouldn't be fair to say it's hard. Hard is walking up a flight of stairs carrying an alligator, right? That's hard. This is just walking up a flight of stairs. You know, and it's, yeah, I mean, you just got, it takes a while, but you can do it. Everybody can do it. So there we have it. So let's just take a breather here. What does anybody want to say or share or ask a question? There's not the worst thing in the world. There's formulas, and you plug the numbers in. Anybody else? Yes, Omar?
For the test, you have to follow this whole step or just like that.
Great question, Omar. For the test, you must follow the instructions. And the instructions will tell you how to solve the problem. If the instructions say find the x-intercepts using the quadratic formula, then that's what you have to do.
Are you going to give us the formula or?
That's a good question. I don't believe that the final exam gives you the quadratic formula. You have to know it off the top of your head. So what I would do, Nadine and everybody, is I would start memorizing that map that we just had drawn. Where is it? Who still has it? That map. Yeah. This nice little graph here, it clearly shows you the x-intercept, the x-intercept, the y-intercept, and the vertex. You want to start memorizing that. And I promise, if you just draw that diagram 10 times in a row, you'll probably have it memorized. All right. Well, folks, you did really good work today. I know we're not done, but that certainly is a resting point, you know, because we accomplished a lot. Any other thoughts or questions? Omar, thanks for your question. Valeria?
No.
Emily? Nadine? All right. Yep. I'm just giving us a second, just in case anybody has anything to think about.
Do you think there's life on the other side of the back side?
I don't think so, but only because the moon doesn't have an atmosphere. They make it very hard. But
I heard like there's like this small pocket where it,
wait, life on the moon? No, it has an atmosphere.
yeah,
Oh, yeah. I mean, the
like
moon
there's
might,
like this small portion like it's breathable.
I
There, I don't know. I have no idea whether it's true.
don't think so. Just off the top of my head, I could be wrong.
I just heard.
I'm not an expert on moon atmosphere, other than the fact that I don't think there is one. Okay, well, yeah, that's fine. So, no, because the dark side of the moon, of course, is lit half the time. It's just we never see that side of the moon. It's a misnomer. It's not the dark side of the moon, it's the side of the moon we never see. Right? It has light. Okay, let's try it out, folks. Word problems. Everybody's second favorite F word, word problems. So let's just start by reading it, because remember, your job is to read it and write down as much as you can. Don't feel too much pressure to solve it. Just feel the need to read it and write down as much as you can. So the average fuel economy F in miles per gallon for passenger cars in the US. Let's stop right there. What is fuel economy in miles per gallon? Okay. Right, yeah, F.
Yes.
That's up to you.
Yeah. Maybe. Do any of you know the miles per gallon your car gets? The miles per gallon your car got?
Yeah. I like
30 miles per gallon. So Gabe drives a Toyota Corolla. He drove a Toyota Corolla, and it got about 30 miles per gallon, right? My wife has a minivan. It gets about 28 miles per gallon. Anybody else know? 12 miles per gallon and what?
Kissel.
A Kia Soul only gets 12 miles per hour?
I think so.
I mean, 12 miles per gallon? Oh my gosh.
I had a 70 thing. Got it.
8 miles per gallon. Ooh, that's a bummer. Anybody else? Now, you know, these days, if you get a hybrid car like a Toyota Prius or something, you get like 40 miles per gallon.
Oh my god, you can go forever on it.
Yeah, you can go a lot. Of course, if you're driving an SUV, or even worse, an RV, you're looking at like 8 miles per gallon, right? So that's what we're talking about. Look again. The average fuel economy F in miles per gallon for passenger cars. Okay, so they're just talking about passenger cars. We're not talking about RVs. We're not talking about buses or semi-trucks. We're just talking about normal cars. And so when we talk about F, whatever F is, it equals a number, like 22, in miles per gallon, which is normally just written as mpg. So, huh?
Nothing. Just that. I wouldn't realize now there's nothing there.
It really doesn't, but I've been doing it for years. So, and I've never fallen either. That's the key.
Okay.
Never yet. So they're giving us this function. So hold on, I want to get the color here. They're giving us a function, and let's really look at it. Now, your first job with the function is to always label the units. And so remember, we're just writing down as much as we can. The function is f of t equals negative 0.0076 t squared plus 0.45 t plus 16. And it says where t is between 0 and 28, we still don't know what t is, where t is the number of years since 1980. So t is the number of years since 1980. So here's what I'd like us to do next. Oh, wait, we have to label everything.
Wait, where's the 22?
I just made it up.
Oh.
Yeah, I was just giving an example. So t, little t, is what?
Number of years since.
Yeah, years since 1980. And f?
Miles per gallon, average.
Yeah, average miles per gallon, right? So everybody label your thing here. But you know that little t is how many years since 1980? So what does t equals 5 mean?
5 years since 1980.
1985. Okay, and then mpg would be whatever, 22 miles per gallon, 8 miles per gallon, 40 miles per gallon. Now this whole computation, when you do that whole computation, what is it going to equal? Miles per gallon, right? F represents miles per gallon, but more importantly, your input is years since 1980. Your output is miles per gallon. Okay, so now what we do is we start a graph. We say, here's my graph. My input is years since 1980. Again, you cannot label things too much. I know the voice in your head is saying, gee, label all these things, you write so much. But it's so helpful, right? So now F is my y-axis, and that's miles per gallon. So now we've got some graph. Now what does my graph look like? Just what's the basic shape of it? It's a parabola, and it's upside down. So we've got an upside down parabola. Just for fun, I'm going to go ahead and go. And what else can we say? Yeah, right? Like in our head now, we're thinking y-intercept, x-intercept, vertex. Well, there's a vertex up here. There's a y-intercept here, And then maybe somewhere over the rainbow, there's an x-intercept over there. And maybe back here, there's an x-intercept as well. So what's the easiest piece of information to find? The y-intercept. What's the y-intercept? 16. It's just the last number C. So we're doing great, folks. Now let's actually finish saying what this means. 16 miles per gallon in what year? 1980. Yeah. Okay, so then, theoretically, as we start ticking 1, 2, 3, and so on, that's really the year 1981. That's the year 1982. So now, folks, I want to call your attention to something. What we've written down here so far is awesome. This looks good. We found the answer yet? No. But it looks great. This is what math looks like. We've really wrapped our mind around what's happening. We really understand what this function means. That if you input a year, it'll tell you the average fuel economy for that year. So we just want to know the vertex. In the interest of time, let's just go ahead and graph it and find out what the vertex is. You could be using the quadratic formula, the vertex formula, but negative 0.0076 x squared plus 0.45x plus 16. Here's my graph. There's my vertex. Let's all write it down. There. Everyone write that down on your vertex. Does everyone see it? 29.605. That's the x-coordinate. 29.605. And then the y-coordinate is 22.661. Now, did we just cheat by using a graphing calculator? Yeah. Theoretically, if this was a problem on a test, you'd have to demonstrate how you got your answer by doing the quadratic formula, the vertex formula. But it says find, we just did, and interpret the coordinates of the vertex. So now let's label. We labeled the function, you label your answer. What does the x value represent? Years. Years since 1980. So this is years. Yeah, exactly. Since 1980. So what year is that? What's 29 years after 1980? Yeah, so in 2009, what? What does that output represent? Yeah, miles per gallon. So this is MPG. So in 2009, the average fuel economy for passenger vehicles in the USA was 22.6 miles per gallon. That is just such a wonderful word problem, folks, because are we doing any earth-shattering mathematics? No, the math is very easy. In reality, what you're doing is knowing what you're talking about. It's taking a little short paragraph, understanding it, labeling everything, drawing it, and being able to tell the next guy what you just found out, or next gal, anyway. Anyway, that's it. We're done with the problem. Which is good because we're out of time. So, thank you very much, folks. It's 2:50. Your homework, the only homework you're responsible for, this we're going into the weekend, is everything from chapter 1, so 1.7 and everything else. And then we're done with 2.2. We just started 2.3. 2.3 is quadratics. We're not quite done with it, so it's not due. But for sure due by Monday is 1.7 and 2.2. And I will update the due dates in the system accordingly so that you only see a due date for 1.7 and 2.2.
Are you collecting these? Are these also due?
I only collect things on the day of the test. So on the day of the test, I will take it from you.